Hello again. This is Math 2245 coming to you from the College page, and the title of this lecture is the Cayley Hamilton theorem and 4 more LSAs. As always, please be attentive while watching this video. By way of introduction, a useful administrative gambit after our break last class was appropriate, but compromised our post-break coverage of material. So as promised, this video plugs that content gap with a very important and more advanced topic known as the Cayley Hamilton theorem. This video also introduces 4 more LSAs. So by way, continuing of introduction, if P of t is equal to C0 plus C1t plus C2t squared plus dot dot dot, thank goodness for dot dot dot, plus Cn Tn, we define P of A to be the matrix formed by replacing each power of t in P of t by the corresponding power of A, with A raised to the 0 power equaling the identity matrix. So that is P of A is equal to C0 times I plus C1 times A plus C2 times A squared plus dot 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 plus Cn times A to the n. The first LSA is show that if lambda is an eigenvalue of A, then one eigenvalue of P of A is P of lambda. A second LSA is also described here. Suppose A is diagonalizable and P of t is the characteristic polynomial of A. Define P of A as above and show that P of A is a 0 matrix. This fact, which is also true for any square matrix, not just one that is diagonalizable, is called the Cayley Hamilton theorem. And for this LSA where you're proving that for a diagonal thing, don't quote the Cayley Hamilton theorem and then apply it to this. You want to prove it from scratch. Okay. Cayley lived from 1821 to 1895 and did a lot of important work in the algebra of matrices, invariants also, which we will talk about later, and also work in non-Euclidean and n-dimensional geometry. Sir William Rowan Hamilton was an Irish mathematician, the most prominent Irish mathematician of the day. He was an astronomer and mathematician, and he developed a technique called quaternions, which was a precursor to what we now called vectors. Now, they knew various versions of these theorems were true, but it was not proven until later, and the first full proof for the Cayley Hamilton theorem was given by Ferdinand George Frobenius. Now, students of Math 2270 will recall the method of Frobenius for singular differential equations, but he actually was more famous for many other things, and he too was an algebraist. So here's a statement of the Cayley Hamilton theorem, and this is one of the most powerful theorems of matrix theory, and we'll look at a proof later. So the theorem states, a matrix satisfies its own characteristic equation. That is, if the characteristic equation of an n by n matrix A is lambda to the n plus an minus 1, lambda to the n minus 1 plus dot dot dot, all the way down to plus a1 lambda plus a0 equals 0, then the matrix A raised to the nth power plus a minus 1 matrix to the raised to the n minus 1 power plus dot 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 plus a1 times the matrix plus a0 times the identity matrix is equal to 0. Again, a matrix satisfies its own characteristic equation. As a getting started example, here's what I will ask you to do. Consider the matrix A a 2 by 2, which is 1, 2, 4, 3, and verify that the Cayley Hamilton theorem does work for this one. And again, to get full benefit, I suggest you hit pause, verify yourself this, and then return. Let's see how you did. So what you do is you figure out what is the characteristic equation. It is lambda squared minus 4 lambda minus 5 is equal to 0. And you check to see if a squared minus 4a minus 51 is equal to the 0 matrix. And if you do the calculation as shown here, you find out that it is there. Now, one of the things that is an element of tradecraft that you've probably already figured out, but I'm asking you to prove it here in this LSA, is for a 2 by 2 matrix, the characteristic polynomial is lambda squared minus the trace of A plus the determinant of A. And clearly that's true here because we have lambda squared, the trace. You add the diagonal elements, you get 4, so it's minus 4 times the trace. And the determinant of this is 3 minus 8, which is minus 5. So clearly it works here, but I ask you to prove this for a general 2 by 2 matrix. And again, this is another LSA. Let's try a bigger problem with the Cayley Hamilton theorem. So this time let's look at a 3 by 3 matrix. 3, 0, minus 1, 2, 0, 1, and 0, 0, 4. Again, I suggest that you pause and verify this for practice. Let's see how you. Now this time the characteristic equation is, I'm leaving it in factored form here, you don't have to, but it is 3 minus lambda times minus lambda times 4 minus lambda equal to 0. So we have 3 times the identity matrix minus A, and 4 times the identity matrix minus A. So if we do those calculations, we find that indeed it does satisfy, and we get 0 for the answer. This the 0 3 by 3 matrix. Now, one immediate consequence of the Cayley Hamilton theorem is a new method, and in fact a better method for finding the inverse of a non-singular matrix. As you know, there are very good ways for us to raise matrices to a power. So if lambda to the n plus a to the n minus a sub n minus 1, lambda to the n minus 1 plus all the way down to a1 lambda plus a0 is equal to 0 is the characteristic equation of a matrix, it follows that the determinant of A is equal to minus 1 to the n times a0. Thus, A is invertible if and only if a0 does not equal to 0. Now, I'm asking you to prove this statement right here because it just said it follows that. So prove this as an LSA. And what we're talking about here as this nice formula for the inverse is one of many applications of the Cayley Hamilton theorem to a very diverse set of technical fields. Okay, so let's go through and see how this works then. So we are taking this to be the characteristic equation of A. Now, we know that A doesn't equal 0 because of the LSA that you're going to prove. So by the Cayley-Hamilton theorem, we know that A raised to the nth power, that is the matrix A, plus a(n minus 1, a to the n minus 1, plus all the way down to, I get a0 times I is equal to 0. Well, I can factor on the left A out of there. And now what I have is that A times whatever matrix this is a multiple of the identity matrix, but I can divide by minus a0, so that means that A is equal to, that A inverse rather, is equal to minus 1 over a0, a(n minus 1 plus a(n minus 2 times a to the n minus 2 all the way down to a1 times I, and that is the identity. So this is an inverse of A. But we know the inverse is unique, and so that means that that definitely is the inverse. That's, of course, the only inverse. Let's see how you understand this. I'm going to ask you to use the Cayley Hamilton theorem to find A inverse for this matrix. Is a 3 by 3. It is 1, minus 2, 4, 0, minus 1, 2, and 2, 0, 3. Again, I suggest you hit pause and verify. Let's see how you did. Okay, so the characteristic equation which you have to come up with is, this time it is lambda cubed minus 3 lambda squared minus 9 lambda plus 3 is equal to 0. So we substitute in, but we know that that has to equal to 0. And so that means that this is equal to minus 3i, and I can factor that out. And so a is equal to a times 1/3 minus a squared plus 3i plus 9i is equal to the identity. And so that means that I can do the calculation of the inverse using this Cayley Hamilton theorem, and I will get that this expression down here is in fact the inverse of A. Now, and this can happen for larger and larger matrices much easier, and so this is an excellent numerical technique. Okay, it's time for the proof of the theorem now. So we begin a proof of the Cayley-Hamilton theorem by noting that if B is an n by n matrix having elements which are polynomials in lambda with constant coefficients, then B can be expressed as a matrix polynomial in lambda whose coefficients are n by n constant matrices. Now you want to think about what that means, but here's an example. And so as an example, consider the following 2 by 2 matrix. So here you have lambda cube all the way down to lambda 4 in that position. This should have been separated better. But the next entry over here in the first row, second column, is 2 lambda cubed plus 3 lambda squared plus 4 lambda plus 5. Here you have 3 lambda cubed plus 4 lambda squared plus 5 lambda. And here you have 2 lambda plus 3. So you see then if you just, I guess I'm going to call that some factorization, but you have the matrix 1, 2, 3, 0 times lambda cubed. There's 1, there's 2, there's the 3, and there's no term here, so that's the 0. That's where that comes from. Plus the next matrix is going to be 2, 3, 4, 0, lambda squared, 3, 4, 5, 2, lambda, and 4, 5, 0, 3. So you see we just can do this with any matrix. So in general, if we start with a B being an n by n matrix, and the elements of B are polynomials of degree k or less, then we can write B as a factored form of capital BK, lambda k, plus bk minus 1, lambda k minus 1, plus all the way down to b1 lambda plus b0. And bj is an n by n constant matrix. Now it doesn't mean all the elements are the same. It could be like this, 1, 2, 3, 0, but it is a constant matrix. Okay, now we proceed with our proof, and we're going to use this technique. So we're going to let A be an arbitrary n by n matrix, and we're going to define A, or we're going to modify A by subtracting lambda I, and we're going to call it C. So C is equal to A minus lambda I. And d of lambda is going to be a polynomial. D of lambda is going to be a representative characteristic polynomial. This is lambda the n plus a n minus 1, lambda n minus 1 plus all the way down to a1 times lambda to the 1, and then that is a0. Okay, so we've defined C thus, and this is D. And again, these are called equations 62 and 63 in the note. Okay, and again, what we're trying to do is we're trying to show that if we take the characteristic polynomial of A, which is going to be defined as the determinant of C, that's going to give us, and I substitute A into that equation, I will get 0. So that's where we're going and what we're doing. Okay, now the C we talked about is an n by n matrix, and so it follows that the elements of CA, and this is the adjoint of C. So let's remind ourselves what the adjoint is. So the adjoint is this CJI, and it's this matrix that looks like this. So it is C11, C21, CN1, C12, C22, CN2, all the way to C1N, C2N, CNN. Now that is that's the transpose, but these coordinates actually are each of them is what we called a cofactor. This is minus 1 to the I plus j times the determinant of ji, because this is the transform. Now you might recall that back in fact we called it theorem 8, The matrix of cofactors is called the adjunct or classical adjoint, and here we're calling it Ca. So we take the adjoint of this, a little bit different notation. So anyway, that's what we're doing. And so we say Ca then is a matrix. Again, it is square. And so that means that what we will have, since by the very construction of this, this will be polynomials of degree n minus 1 or n minus 2. Now, elements on the diagonal of this one will be polynomials of degree n minus 1, while all the others will be polynomials of degree n minus 2. So, by the work that we did previously, we can decompose or factor or represent Ca as Ca is equal to Cn minus 1 lambda n minus 1. Cn minus 2 is times lambda n minus 2 plus all the way down to C1 lambda plus C2. We can get that representation. And we had a theorem 8 from long ago, earlier in the course, is that if we have A was an invertible matrix, then a formula for A inverse is 1 over the determinant of A times the adjoint of A. While translating that to our current situation, we have that Ca times C is going to be the determinant of what we called C times I, but the determinant of C is the polynomial d of I. So you see what that means is that from 62, that previous theorem, we have that this times this is equal to Ca. C was A minus lambda I. I can distribute the adjoint, and what I will get is C raised to the Ca, the adjoint, times A minus lambda Ca. And so I can equate one term from 60, the left-hand side here, with this, and I have that d of lambda I is equal to this product. But now what we have is we have two polynomials, and we're going to declare that both sides of this equation are matrix polynomials of degree n. And since two polynomials are equal, if and only if their corresponding coefficients are equal, we have that I is equal to minus Cn minus 1. And we have An minus 1 times I is minus Cn minus 2 plus An times I, dot, 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 all the way down to A0 I equal C0A. Now you want to make sure you understand and verify what's spoken of in 69 here. But we're almost finished. Because we'll multiply the first equation by a to the n, the second equation, both sides, by an minus 1, and the last equation by a0, which is the identity matrix, and then we will add. But you see, if you look at these expressions, you're going to see that there's a telescoping that goes on, and everything will cancel out on this side, and on the other side you will have this expression, the matrix A raised to the n plus a n minus 1, a n minus 1 plus all the way down, and so on, equal to 0. You see, this is an elegant proof of the Cayley Hamilton theorem, and we didn't need for the matrix to be diagonalizable in order to do this work. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself, because self-care is important. And now more than ever, take care of each other, because we're all in this together. Look forward to seeing you in class. Till then, God bless you all.